Morning. Welcome to today's class. It is lecture number 2 in unit number 3. So Mos layers that we talked about. Mos layers and stick diagrams. Stick diagrams. What we have seen in the last class? The last class we have seen a realization of the digital circuits. You can say that digital circuits, three fundamental circuits using NMOS and CMOS technology. So this is what we have seen in the last class, right? So by using the NMOS symbol, by using the PMOS symbols, we have realized the circuit. Okay, but actually, if you want to fabricate, these transistors on a silicon chip, okay, layer information is very important than that of the circuit symbolic representation. Okay, so that means we have to draw the layer information. We have to draw the circuit in the form of layers. In the form of layers, that layered information is suitable, or it is required for fabrication of circuit on a silicon chip, right? So, so what are the different layers that we can see for a particular transistor? Okay, the essential. So that means that instead of saying that whatever the circuit I have, so far I have seen by using the symbolic representation of NMOS transistor and PMOS transistor, that is materialized by the Mos layers. Okay, so therefore now we are going to see now the symbolic representation of circuits, okay, using the above technologies. Okay, the symbolic representation of the circuit is materialized by a layer information, by layers. Clear? So therefore the layers are very important now for the circuits whatever we have that are represented in NMOS and PMOS symbolic representations. What we have seen this NMOS and CMOS representations, normally these are the symbols that I have used for NMOS, and this is for the PMOS. Okay, this is for depletion type mode transistor. Okay, something like this we have seen, but now we are going to use some layers. So what do you mean by a layer in this one? Okay, so that is the concept called Mos layers. Mos layers. So let us consider a MOS transistor layer. Actually, the MOS layers in the sense MOSFET layers or MOS transistor layers. So what are the essential layers that we use, or what are the essential materials that we use for MOS transistor? What are the essential materials or layers that we use? Layers or material, both are the same, so one and the same. Okay, so what are the materials that we have used for MOSFET transistor, MOS field effect transistor? Okay, so let us consider, we have already discussed this point. Okay, so we have, for example, NMOS transistor. You consider NMOS transistor. Here we have to consider a substrate. Okay, on top of it we have a polysilicon. On top of it we have a polysilicon, sorry, gate oxide. On top of it we have a polysilicon. Okay, so therefore the substrate is one material that we are using, right? And gate oxide is one material that we are using. Polysilicon is another material we are using. And diffusion is another material that we are using, right? And metal layers that we are using the metal layers also. Okay, metal contacts. Okay, so out of all these things, for a particular MOSFET, what are the essential layers, essential materials? What are the essential materials that we use? Okay, so answer to this question is, the first number one is polysilicon. Polysilicon is the one essential material or essential layer for MOSFET, right? The second one is diffusion. Second one is diffusion. The diffusion can be N diffusion, N diffusion maybe, or P diffusion, or maybe P diffusion, whatever it may be. Third one is metal. Third one is metal. So out of all these, whatever all the materials that we use in MOSFET, these are the essential materials that normally we use for a transistor. So I can simply write here is essential layers. Essential layers. Okay, so we want to translate the symbolic representation of the circuit into a layered representation. So our objective is that converting a symbolic representation of circuit into layered representation. So this representation is very useful further to implement our circuit in representation of the circuit into the silicon chip. Okay, so therefore layer information is an essential way of presenting your circuit. Layer information, layered representation. Okay, so how do we do this one? So this is done with the help of three important concepts. How do we translate this one? This is done with the help of three important concepts. So the concepts are number one, stick diagram. Second one is we need to talk about the design rules. The third one is layout. So these concepts are very essential. Normally, the layer information, we put it in the form of a layout. This layout information, we have to give it to the fabrication engineer, and fabrication will be done on a silicon chip. Okay, so but we cannot go directly to the layout without using the design rule concept, without knowing the stick diagram concept. Okay, so first of all, we should know the basic background of about two concepts. Then only we can go for the layout drawing the layout of your circuit. Is it clear to all of you? What is our objective is? Fine. Now let us talk about what do we mean by a stick diagram. Okay, stick diagram. Okay, so therefore it is also a simple diagram which represents the circuit in the form of color codes. Represent the circuit which is in the form of layers will be represented by color codes. Okay, so the layered information, I can write it layered representation, layered representation of circuit is presented with color codes. So very important, color codes. Color codes that we have to use. Okay, what does it mean? For example, as I mentioned that what is the layer that we normally use for the polysilicon? For the polysilicon, we have to use a layer, is a one type of layer, so that is represented by a red color. A simple one line is representing a polysilicon. Simply we're representing by polysilicon. So therefore red color that we have to use for polysilicon. Similarly, for the end diffusion, I have to use green color. So green is the color that we have to use for end diffusion. Similarly, for the P diffusion, we use yellow color. We use more colors, yellow. We use yellow color. Sorry, just a second. Okay, I think this is an yellow color. I can write it. It's an yellow color. Okay, for metal, I am going to use blue color. So blue color. Okay. We have these the contacts also. Contacts. For this one, I'm going to use a dot, which is a black color. So dot we have to use, which is a black color. Okay. So these are the color codes that I have to use for representing a circuit in the layered form, which is known as a stick diagram. Right? Clear? Now let us draw the stick diagram for a simple transistor, and from the transistor to the circuit. How do we draw this one? Let us look at this one. Okay, stick diagram for an NMOS, stick diagram for MOSFETs. Okay, I'll write here. Stick diagrams for MOSFETs. Stick diagrams for MOSFETs. Right? Stick diagram for MOSFETs. For example, an NMOS transistor, let us consider an NMOS MOSFET. Okay. So, but what we can look at in this one, that means stick means it's not bending point. Okay, stick is not a bended one, so it is a straight one. Okay, so therefore, whenever you draw a particular color, it must be a straight line. Okay, it is a horizontal line or it may be a vertical line. It should not be curved one. Okay, please remember that part. So look at this MOSFET here. So here you can observe that horizontally the diffusion is available. Okay, vertically there is a polysilicon is existed. So whenever a end diffusion line is crossed, Whenever the polysilicon is crossing this N diffusion line, then we can say that the transistor is formed there. Okay, that means the diffusion here is in horizontal fashion and polysilicon is in the vertical fashion. Okay, therefore, whenever these two colors are crossed together, crossed at the particular point, then we can simply resemblance of this representation is nothing but a transistor is formed. Right? So therefore, what I can say that, so in a stick diagram, so normally what is the symbolic representation of this device? Something like this. Okay, so this is an NMOS transistor in symbolic nature, symbolic position. But now in the stick diagram, so we can say that this is the source, this is the drain, this is the gate. Okay, diffusions are at source and drain. That means diffusions are at the horizontal position, one line, some line. So the thickness and how much length is not matter here, but meaningful way that we can draw it. Okay, and when the red line is crossing this one, then this is called a transistor. Stick diagram of NMOS transistor. Okay, this is the circuit symbol. We write it here is in this form of something like this. It's a circuit symbol. Circuit symbol. It is a stick diagram. Stick diagram. Okay, is it clear to all of you? Similarly, so of course there may be a possibility. Another possibility is that this way also we can look at. So here in this case, what is the position of the source and drain? Vertically. What is the position of the polysilicon? Horizontally. So the moment what you have to observe is that whenever a polysilicon is crossing the diffusion line, or whenever the green line is crossing the red line, or red line is crossing the green line, the transistor will be formed. Clear? So therefore, that's what we have to remember. So the orientation is not an important. The thing is that when when red line is crossing the green line is crossing the red line, transistor will be formed, undoubtedly. Okay. Similarly, let us write for PMOS. How the PMOS will look like? Something like this. It's a bubble that we normally use. What is the stick diagram here is that we have to use yellow color, and we have to use red line over there. In the examination also, we have to use these colors. Please remember. So, or otherwise the orientation you can change, you can write it also. That one also is possible. Okay. Another one we have to write here is depletion NMOS. Depletion NMOS. So far we have seen enhancement mode NMOS and PMOS that we have seen. Okay. Sometimes the circuit consisting of depletion mode type of transistor also. Therefore, we have to notice and we have to mention its stick diagram as well. Okay. So what we do in this case? Okay. Normally, what is the symbolic representation? We know in this one, in this way. The thick line that we have to use for this line and something like this. Okay. So this is a symbolic representation. So this is that means the channel we have to show here. Channel we have to show here. Right? So therefore, in this sense, what we have to do, it is NMOS transistor. Therefore, diffusion is green color. Polysilicon is also there. The polysilicon is red color. Now here, the implantation we want to mention. Okay, so we want to mention the ion implantation technique that we have to use for the channel channel formation. Okay, for that one, dotted yellow colors that we have to use something like this. Dotted yellow colors that we have to use something like this. Okay, so by looking at this diagram, we can say that it is a depletion mode transistor. It is a depletion mode type of transistor. Is it clear to all of you? How we are using this representations? The MOS transistors, NMOS, PMOS, and depletion NMOS transistor. Okay. Please let me know if there is any doubt, if it is clear. If you say yes in the chat box, so that I will move further. Somebody please respond. Is it clear to all of you, those who are present in the class? Stick diagrams. Okay. So far so good. Okay, now let us take a simple inverter. Then how do we draw the stick diagram for an inverter? Okay, fine. CMOS inverter stick diagram. Not CMOS, for example, NMOS we consider. NMOS inverter stick diagram. Stick diagram. Okay, NMOS transistor stick diagram. What is the symbolic represent circuit symbol for the NMOS inverter? So this is the logic representation. This is the logic representation. Okay, the circuit representation is something like this. We have a depletion mode type of transistor. We have NMOS transistor. Connect these 2 points. Connected to ground. Connected to VDD. And this must be source and drain must be at the same potential. Take a common point. This is called Vout. This is called VIN. Okay. So this is the circuit symbol. Now I want to convert this circuit symbol into stick diagram. What I have to do? So the procedure is the same for every circuit. Just you have to follow that procedure. Okay. Drawing the stick diagram is different approaches are there, but we will consider only the basic approach. Okay. So in this basic approach, first of all, we have to draw the metal lines for the VDD and ground. Okay, it's very important to consider that. Okay, as we have mentioned that polysilicon is, we have used polysilicon material and diffusion, p-diffusion metal. For metals, for what purpose we use? That's important one. Okay, so that's what I want to write it here. A small note I want to keep it here. Note. Metal is used for interconnections, as everybody knows that interconnections and power rails. So for these two cases, we have to use the metal lines. Of course, can't we use the polysilicon for the connection? Yes, sometimes we use that one. Can't we use the diffusion for the connectivity? Yes, sometimes we use that. But there is a problem with that one for connection purpose. For example, if the 2 transistors are there, these 2 transistors are connected by a simple wire. That is a metal that I have to use. Can't we use any other material to connect the 2 transistors? Yes, it is possible to connect by using the polysilicon by diffusion. But there is a problem with that one. The sheet resistance of those materials are very, very high. Automatically, delay will be increases. Spark and emission also will increases. Therefore, we don't want to go for it. So interconnection means we have to use the metal only. Okay. In addition to the interconnection, power rails also will be implemented by using the metal lines. Okay. So we have to keep this in our mind. Now let us draw this one. Okay. So VDD and ground is nothing but power rails. So I have to take a power rails here. One line for the VDD. One line is for ground. First of all, I have to consider 2 lines. One line is meant for, blue line is meant for VDD power line. Ground for another blue line. Now we can see that the diffusion is available for the N1 transistor, N1 and for example, this is N2 transistor. First of all, I have to draw the power lines. Then I have to form the transistors. As you can see from the circuit, what it is there here. So diffusion is horizontal, something like this. Polysilicon is vertical. Okay. Therefore, what I can do is that diffusion is horizontal. Sorry, diffusion vertical. Polysilicon is horizontal. The transistor is formed there. Similarly, at the bottom, we considered the diffusion at the top, vertical, and polysilicon at this in this way. Now the second point is that form the transistors. The first one is form the power lines. The second one is form the transistors. Right. Now this transistor one diffusion is connected to power line. Therefore, we have to connect this we have to connect this diffusion to metal line. So how do we do this one? So something like this. Just simply I can extend this point to this one. Okay, I can extend this diffusion line towards the VDD line. Here also I'm going to extend my diffusion towards the ground line. Now these two lines are connected together. Okay, but there is no connectivity between the metal and diffusion here, because these are the two different materials. Only the possibility is that when a green line is crossing a red line without using any contact, there is a connection is established there. That's what you have to keep in your mind. But whereas other materials, diffusion and metal, these are two different materials. Unless otherwise, if you're not providing any kind of metal contact, it is not at all connected. Okay, therefore, for contact, black dot I have to use. Is it clear to all of you? Black dot I have to use. Similarly, at the bottom also I have to use black dot, because these two diffusion and the metal are two different materials. There should be a connection is required. Contact is required. Okay. So according to the circuit diagram, so this top diffusion, so this diffusion is connected to this diffusion. Okay. Between these two, we can use the metal, or we can use directly extend the diffusion, because the both are the same materials only. Therefore, I can simply extend this diffusion towards this diffusion, because both are same. The question is that, is it necessary to provide a diffusion here, the contact here? Obviously not required. Why it is not required? Because the same material. So when the same material is crossing, for example, one diffusion here, another diffusion here. So even if you're not providing any kind of contact cut here, the connection will be established. Suppose something like this. It's kind of something like this. So these two are very near to each other. Therefore, there is automatically the connection is established between these two. Whereas if it is a diffusion, if it is a metal, unless otherwise it is a diffusion, and this is a metal and diffusion, unless otherwise, if you don't have any contact here, there is not at all connected. So we can say that connected here. So with the help of dot, connected without using contact, because same material. Here also connected. Here also connected. Why? Because same material. So when the same material is crossing another same material, automatically connection is established. Otherwise, two different materials are, if you want to connect it, contact cut is required. Okay, you have to keep that in your mind. That's it. Now I can extend this. What I have to do is that I don't need this contact, right? So directly I can extend this diffusion from here to here. Okay. Now this is how one connection is established. Another connection is the gate of this transistor is connected to the source drain of this transistor. Sorry, the source is connected to the gate of the transistor. That means I'm extending this polysilicon from this point to this point. See, observe carefully here. You have to observe very carefully one point. Whenever a red line is crossing the green line, transistor is formed here. But here what we are observing that if I'm using the metal, I don't have any problem. So from here to here, if I'm using the metal, okay. If I'm using from here to here, for example, here to here metal, if I'm using it, I don't have any problem. But usual practice is that whenever we have a depletion type mode transistor as a load, the polysilicon is we're extending towards the diffusion side. That's what we normally do. In that sense, but the problem is the transistor will form, but our requirement is not a transistor. Here actually contact is required. So for that one, we have to use buried contact. What we have to use? We have to use buried contact. How do we look the buried contact? It's a brown color that I have to use, brown color. So brown color, please remember that, a brown color contact. So what we can call it as this, what we call it as buried contact. Buried contact. Okay. So therefore, only the output is pending. So I can extend this line to this one. So this will be considered as no need to mention its names also, but just for the sake of simplicity, I am writing. This is the V out. This is the VAN, and this is the VDD line. So this is called VDD line. This is called ground line. That's it. Okay. This is the stick diagram for the NMOS inverter. This is the stick diagram for NMOS inverter. Don't forget to write one point. One point is that whenever we are, normally these transistors are there in the substrate, right? Substrate also we should mention with the help of black color cross. With the help of black color cross, that means the substrate is there for these transistors. That's what we have to mention. Okay. So very simple to understand actually. Okay. Shall we write for the CMOS NOR gate? Sorry, not CMOS NOR gate, NMOS NOR gate. Let us draw the stick diagram for NMOS NOR gate. Okay. CMOS, sorry, NMOS NOR gate. NMOS NOR gate stick diagram. See, by the way, just if you want to have an AND gate, for example, what I have to do, NMOS NAND gate, just I have to use another transistor at the bottom. Here I need to consider another transistor, right? So here another transistor, that means we have to draw another line here, that's all. So another red line is we have to use there. But you have to give the space between that one. Okay, don't write it very near to each other, but there is a space that we have to require. Okay, for the simplicity, I'll write it here for the sake of understanding. Just to please remember, for the NAND gate means just we have to use 2 polysilicons. That's it. It will be acting as an AND gate. Okay. Therefore, this is called VAN1. This is called VAN2. Or example A or B also we can consider. Please remember, this is the NAND gate. NMOS NAND gate. NMOS transistor NAND gate. Okay, so therefore for completeness, I'm not going to do that one. So I'll do let it be keep like not gate only. Okay, for different way that I want to write it for this one. So what is the logical representation of the NOR gate? This is the water. What is the circuit symbol for the NOR gate? I have to consider. This is the VDD. NOR means, as we have seen in the previous class, 2 NMOS transistors are connected in parallel. 2 NMOS transistors are connected in parallel. So this pull down is connected to ground. This is called V out. Let me call this is A and this is called B. Okay, now what I can do here is now simple, just within 2 minutes I can write it. So I have to take the power lines by VDD and ground. Okay, that is the first point. The second point is the diffusion lines I have to draw. So one diffusion here. Okay, another diffusion is here, another diffusion is here, right? So I have to cross a polysilicon over there so that it will be acting as a transistor. Therefore, the three transistors I have shown. Now provide the connections between these two. So see, normally, since these are all the same materials, same transistors, so NMOS transistor I'm using, that's the reason why I'm extending the diffusion. Otherwise, connection between the transistors, we should use metal lines only. Okay. So therefore, since these are all the same material, I'm extending this one to this one. I'm extending this one. I'm extending to this one also. Okay, and connected these two things with the help of the same diffusion because the same material. I'm extending this one also same material. Therefore, all these three layers are connected to each other. Now another connection is polysilicon must be connected here. Okay, and we have to provide a buried contact over there. I have to provide the buried contact in this particular place. Okay, brown color I have to use, and I have to use a black color for this one, black color for this one, black color for this one. Okay, just I have to extend this diffusion line as a V out, and these are the A signal, and this is called D signal. That's it. And I have to show the crossbar for diffusions, sorry, substrates. Okay, you have a question here. Sir, here I have connected these two things, right? These two things are connected and connected to common point. Yes, it is also possible to connect something like this. These two are connected and take a common point here. Therefore, only one contact is sufficient for that. In that case, it is also, we can do it. But purposefully, I have done like this. Just you have to mention this way. I will tell you that point later. Okay, this is the stick diagram for NAND gate. For like this, we can draw anything. For example, so for simplicity, I'm writing, for example, OR gate, I want to write it. Stick diagram for OR gate. What do we mean by the OR gate? What do I have to do? For OR gate means, first I have to draw the NOR gate, and we have to add the inverter at the end. Okay, so therefore I'm going to take this one. So copy, I can paste it here. Okay, this is a NOR. So what I have to do is that I have to connect the inverter at the end. So I have to take the NOT gate stick diagram. So I have to take NOT gate stick diagram. So this is the NOT gate stick diagram. Here. Luckily, the widths and same things I have followed. Interesting. So these things are not necessary to show. So it's a buried contact. So therefore, this is a. Now, how do we provide the VN to V out to VN? So now it's very important. Okay, these things are not required. Okay, and just only have to connect it something like this. This V out is must be connected to the. Sorry. So this V out is connected to the VN of this one. Please remember. So I have to connect this green line towards the red line. Okay, towards the red line, or I have to extend the polysilicon towards the green side. In this situation, metal is very suitable one. In this situation, metal contact is suitable one. Okay, so therefore I'm going to use a metal line here. It is a stick, so I cannot draw something like this. I cannot draw something like this. Okay, please remember, stick means something like this only. So I have to extend this one extend this, and extend this point. Clear? Now the question is that here the metal is connected to the diffusion, polysilicon is connected to the diffusion. So what things are required here? Contacts are required. As simple as that. Contacts are required. So what kind of contacts? So simple contact is required. For that one, black dot is required here. For this one, black dot is required at this point also. Okay. I hope the things are clear. So therefore, this is the NOR. This is the NOR gate. This is the NOT gate. So overall, this is considered as OR gate. Overall, this is OR gate stick diagram. So I hope you understand this problem. Okay. So this is how we have to draw the stick diagram for any circuit. Okay. Whenever we have whatever the circuit I give, for example, AB plus C. Okay. So the stick diagram can be drawn very easily. So please remember that once you know the stick diagram, then only it is possible to draw the layout. Without knowing the stick diagram, it is not possible to draw the layout diagram. So you should know the layout diagram, stick diagram very. You should know. You should learn this one. Otherwise, it's sometimes very difficult to learn the layout. Okay. We stopped here today. We will see the remaining things in the next class. One